OCR A, A-level physics. This is for circular motion and SHM. First video, and it's about circular motion. So, uniform circular motion. What is that then? Well, it's motion in a circle, so constant radius at a constant speed. Why do we look at it? Because there's lots of things in nature and lots of man-made stuff that goes round in circles, and so we need to analyze it and understand it. The orbits of planets and satellites. Now, the orbit of planets such as the Earth, it's actually an ellipse, but it's almost a circle. Okay, it's not a very eccentric ellipse, it's almost a circle. The orbit of satellites, when you go on to gravitation, we'll use a lot of these equations. An electron around a nucleus, if you think of an electron as being a particle, then it orbits the nucleus. Particles in the Large Hadron Collider. When you do magnetic fields, we'll talk about charged particles moving in a magnetic field going round in circles, and even cars on a roundabout. It doesn't have to be a complete circle, it just could be part of a circle. So there's lots of examples of uniform circular motion. So let's define some terms here. So we've got the radius of the circle, r, we've got the velocity. Now the instantaneous velocity, because obviously the direction is changing all the time, but the velocity, which is going to be tangential, or the speed, which we have said is constant. We've also got the angular velocity, which is omega, and that's radians per second. The angular velocity is the angle which is swept out every second, so delta theta over time. Yeah, the angular velocity omega, very important. The period t and the frequency, which is in hertz, which is 1 over the period. So these equations in the boxes, make sure you learn them. You need them for circular motion. We're going to use them in SHM, we're going to use them in gravitation, we're going to use them, as I said, when we do magnetic fields. You need to know these equations. So period is 1 over the frequency. Omega is 2 pi over t. So I said omega is delta theta over time. So if theta is 2 pi radians, and the period, the time is equal to the period, then omega equals 2 pi over t. If we substitute for t, we get omega equals 2 pi f, which is a very useful equation. Omega equals 2 pi f. Then for 1 revolution, velocity is distance over time. So 2 pi r over the period. So v equals omega r. Learn these equations. There's another equation we're going to be coming up with soon, but we'll get to that in a bit. Here's a little sum for you to have a go at. Pause the video, pen, paper, calculator, and the answer is in 3, 2, 1. There you go. Okay, big question. Is this object accelerating? So there's an object moving at a constant speed. Is it accelerating? And the answer is yes. Okay, now if the velocity of an object is changing, then from Newton's second law, it is accelerating. Now, fair enough, the magnitude of the velocity is constant. In other words, the speed is constant, but the direction is constantly changing. Okay, if I get my pen up. So the direction of the velocity, it's there, and then it's there, and then it's there. So the direction is changing. Therefore, it is accelerating. Its velocity is changing. In what direction is it accelerating? Well, looking at the arrows, you should be able to see that it's being pulled towards the middle. So the acceleration is towards the middle. It is centripetal. The word centripetal is towards the middle. We are not going to use the word centrifugal. It's a very confusing word. The object which is moving in a circle, the acceleration is centripetal. the force acting on it is centripetal. From Newton's second law, there must be a resultant force acting on the object, and that must also be centripetal. Okay, remember, if an object is moving in a circle, it is accelerating, there must be a resultant force acting on it, and the resultant force is centripetal. In other words, it is towards the center. The resultant force is towards the center. So, examples of this resultant force. Well, what provides the centripetal force in each of these cases? Pause the video and have a think about it for yourself, and I'll tell you the answer now. So, a satellite in orbit, what force is pulling it towards the middle of the circle? And it is the force due to gravity. Yes, so that is the centripetal force. The car on a bend, what force is pulling it towards the middle? And it is friction. Okay, friction between the tires and the road is pulling it towards the center. If you imagine there wasn't any friction, or if there wasn't enough friction, then the car might kind of fly off at a tangent and fall down a valley or something. So it is friction in that case. The electron in an atom, what is the centripetal force? Well, it's the electrostatic attraction. Yes, positive, negative attraction. It is attracted towards the center. Again, there's a force acting on the nucleus, but I don't care about that. I'm only interested in the force that is acting on the object which is moving in a circle, and that force is centripetal. The hammer, well, the hammer is this big metal ball at the end. The force towards the center of the circle is the tension, so the tension in the chain. A roller coaster going over a hump, well, so if that's my circle, the force towards the center of the circle is the weight of the roller coaster. So the weight of the roller coaster is the centripetal force. Then on a sticky wall at the fair, this person here, this guy here, yeah, Fred, what's the force acting on him? Well, it's the push of the wall, the contact force. The wall is pushing him towards the center of the circle. So in each of these cases, the resultant force is centripetal. And in each of them, there's a different resultant force pulling it towards the middle, or pushing it in the last case. A couple more equations. Centripetal acceleration. I'm not going to derive this equation. You don't need to be able to, and the derivation is a little bit tricky, so I'm not going to do it. A equals v squared over r, or because v is omega r, you get A is omega squared r. And that is the equation for centripetal acceleration. Have a go at this question here. So pause the video, pen, paper, calculator, and the answers are in 3, 2, 1. There you go. Note the last one there. Now that we have the acceleration, the resultant force F equals ma. Here's a couple of more questions to have a think about. What provides the centripetal force that keeps this child moving in a circle? So this fella here, Eric, yeah, he's going around in a circle. So there is a resultant centripetal force. Well, the centripetal force would be friction between his bum and the roundabout. You can also see that he's holding on as well. So that's an extra force pulling towards the middle. Some big boys come along and spin the roundabout very fast. They might even use their moped to do it. Describe what is likely to happen to the child. Well, they'll be hanging on for dear life, but if it's going around very, very fast, they won't be able to provide enough centripetal force, and he'll probably go flying off at a tangent and land on a big comfy mattress. Here's another one. This is an interesting one. This car of mass doodah is driving on a level road at a steady speed of thingy. Identify the vertical forces acting on it and state their values. Well, the vertical forces, you've got the weight of the car, and then you've got the normal contact force, and vertically at the moment it's in equilibrium, so those forces will be equal and opposite. So the weight of the car and then the normal contact force will be the same in the opposite direction. Now the car drives over a hump of radius 20 meters at 11 meters per second. Calculate the magnitude of the vertical forces acting on it now. Now it's moving in a circle, and that means that the resultant force must be towards the center of the circle. So the weight of the car is the same as it was before, because we're still on planet Earth. So the normal contact force must be smaller. Why? Because there must be a resultant force, and the resultant force is going to be W minus N. That will be the resultant force. So W minus N equals mv squared over r. Rearrange that for N, and we get N is 5,625 newtons. Notice that the normal contact force is smaller. And in fact, if the car goes faster, then the normal contact force will get even smaller. At what speed would the car leave the road? Have a go at that yourself. At what speed would the car leave the road? And it would be at, when n equals 0, so 14 meters per second. Basically what happens is that the car goes into orbit, flies off the road. One last point about these centripetal forces. Now, this centripetal force, it will change the direction that the object is moving in, but it doesn't change its speed. Therefore, it does not change its kinetic energy. This force acting on the satellite, okay, what it's doing is it's keeping the satellite in orbit, but it's not doing any work. Ignoring air resistance, that satellite will be going round the Earth for many, many, many years. Okay, it doesn't get closer to the Earth. So work is force times the distance moved in the direction of the force. If ever you're asked for the equation for work, yeah, work is force times distance moved in the direction of the force. As the satellite doesn't get closer to the Earth, the force doesn't do any work because the distance moved in the direction of the force is 0. Centripetal forces do not do work. Okay, the pull of the Earth's gravity keeps the satellite in orbit, but it does not increase the kinetic energy of the satellite. Unless the satellite gets closer to the Earth, this force doesn't do any work.